All right, welcome to the Chapter 8 Homework A review. If you're keeping track of where we are in the course, we have basically just 2 chapters left. So Chapter 8 has 2 assignments, the one that I'm going to be reviewing today and one more next week. And then we have consolidated all of Chapter 9 into a single assignment with some of the omitted material that I informed you about last week. So we are getting close to the end, in this week's assignment, we did reasonably well overall. Average was 9.78 out of 12. And there's just a few different problems that I want to go through that we had a little bit of trouble with. Mainly the numerical problems, ones that we had to calculate and answer. And those typically have lower success rates in general, but I just want to make sure that I introduce the different types of problems and how to approach them. So there were several problems in this assignment, and this was something that I did not cover in great detail in the lecture, so I required you to figure out some things on your own, and I'll go over it a little bit more carefully, that deal with measuring pressure in a barometer. So a barometer or a manometer, which are the 2 different pressure measuring devices. A barometer measures atmospheric pressure, as you likely know if you're a weather nerd. But then a manometer measures a closed sample of a gas, which is more used in sort of a research setting. All right, so if in this problem we have the barometric pressure was 1.05 atmospheres, when the mercury level in an open-ended manometer connected to a flask of gas was 126 millimeters of mercury higher on the side open to the atmosphere than on the flask side, what was the pressure of the gas in torr? All right, so there's a lot going on, a pretty long sentence question here. So the first thing we have to realize is that in problems like this that deal with an open-end manometer, you're going to also need to know what the atmospheric pressure is. So barometric pressure is sort of synonymous with atmospheric pressure. Barometric pressure is the pressure you measure with a barometer. So that means that this number here is the pressure of the atmosphere, 1.05 atmospheres. And then we know that we're told that the mercury level is 126 millimeters higher on the side open to the atmosphere than on the flask side. So what's helpful to do, and as I think we give you the hint here, is to sketch the apparatus to figure out what do we do with these different numbers that we have. So in an open-end manometer, and you guys know that my artistic skills are mediocre at best, so I'll try my best to draw one here. You have a flask of a gas, and then it's going to be connected to sort of a U-shaped tube. So you're going to have sort of this shape going on. So it's all glass, but that's not the important part. All right, so then in an open-ended manometer, that means this side is completely open, you're going to have atmospheric pressure pushing down on one side. So this glass is going to be filled with mercury, which I'll draw here in a second. And then you're going to have the pressure of the gas pushing up in the other direction. So basically these 2 pressures are opposing each other. Pressure of the gas pushing up, pressure of the atmosphere pushing down. If the 2 were equal to each other, then the mercury levels would be the same on both sides of the U-shaped tube. But if they're different, then there's going to be a height difference, and that's what we have here. So here we're told that it's 126 millimeters higher on the side open to the atmosphere. So that means we have this situation. The level is going to be somewhere there for atmosphere and somewhere lower on the side closest to the gas container. And so what I'm shading in here is basically what the mercury column would look like, higher on the side open to atmosphere than over here. So what this means, if you think about it, is sort of in sort of physics terms, that the gas is pushing harder than the atmosphere to be able to create this imbalance where the mercury column is lower on this side than it is on this side. So in this case, what we know is that the gas pressure is greater than atmospheric pressure. And more specifically, it's going to be greater by the height difference. So this difference between the 2, which is delta H, is going to be the difference in the pressure between the 2 sides. And so what that means is that the gas pressure in this case is going to be the atmospheric pressure plus the difference in height. Generally speaking, for an open-end manometer, the gas pressure is atmospheric pressure plus or minus delta H. Whether you use the plus or the minus depends on which one's higher. In this case, the gas pressure is higher, so we're going to add the difference to that. Now, the other thing that's important to recognize in these problems is that the 2 units, millimeters of mercury and torr, are equivalent to each other. So we don't have to do any numerical conversions to use those different things, but what we do need to do is we need to get our atmospheric pressure in the right units of torr to start with. So the atmospheric pressure in this case is 1.05 atm atmospheres, but we have to convert that to torr first, which is 760 torr in 1 atmosphere. So that's sort of the key pressure conversion that you're going to have to do a lot in this chapter, in this section of the course. So that comes out to 798 torr, so that's our atmospheric pressure. And then if we want to figure out what the pressure of the gas is, again, the pressure of the gas in this case is going to be the atmospheric pressure plus the difference in height, which is going to be 798 millimeters of mercury, and then the difference in height is 126, so we're going to add that 126. And so what we get is 924 millimeters of mercury, which is the same as 924 torr. Again, those two units are equivalent quantities, just written in two different ways. So this time would be 924 torr. You'd enter the answer in whatever format Blackboard asks you to do. But that's how we approach these manometer problems. It does help to sketch out the device to figure out if you need to add or subtract delta H. So that's for open-ended manometers. If it's a closed-ended manometer, it's actually easier. You don't have to even include the atmospheric pressure. But for this one, we have to account for that. Okay, so that's really the only one I want to go through about pressure measurement. Not a huge focus of this chapter, but something that did come up and could come up on the exam. The rest of these are going to primarily deal with the ideal gas law. So the first type here, there's going to be sort of two variations in gas law problems, I suppose. So the first major type is what we have here, which is where you're given some of the parameters for a gas, moles, volume, temperature, and you're asked to solve for another one, in this case pressure. So in that case, you just have one sample of gas, the conditions are all one set of numbers, and you just have to solve for an unknown. Then the other major type, which we'll get to here next, is one where you have a change in one or more of these parameters, and you're trying to figure out how does that affect then the condition of the gas. And so we'll get to that here in a second. But this one here, we're just given one set of conditions, a certain number of moles, a certain volume, a certain temperature, and we're asked to solve for pressure. So recall that the ideal gas equation, the one that's going to be really the most important one in this chapter, is PV equals nRT, where you have P is pressure, V is volume, N is number of moles, T is temperature. So those really, it's called an equation of state because those are the only four things you need to know about a gas. Pressure, volume, number of moles, and temperature. R is a constant. So in this problem here, what we have is we know how many moles we have, we know the volume, and then we know the temperature. And so what we're going to do is just solve for the unknown pressure as our unknown in this problem. So all we're doing in this problem is just rearranging and saying that pressure is equal to nRT over V, solving for the unknown, and then we can just plug in the numbers. Now the key thing to do in these ideal gas problems is when we're using R, the universal gas constant, we need to make sure we keep straight what units that's in. So we're going to have R is going to be 0.0821 liter atmospheres over K mole. And so what this means is that if we're using R, volume has to be in liter, pressure has to be in atmospheres, number of moles, of course, is in moles, temperature has to be in Kelvin. The temperature for any gas law problem has to be Kelvin. There's no exceptions to that. You can play around with the volume and pressure units in some cases, as we'll see, but if you're using the value of R, it has these specific units, and so those are the ones we want to use. So what we need is we need to probably do some conversions here. So nRT over V, number of moles is given, so that we have 7.88 times 10 to the minus 3. R is the constant, so that's going to stay the same. This is on your periodic table, so you don't have to learn it, but you will learn it if you use it enough. And then here, though, we have to put temperature into Kelvin and volume into liters, neither of those being true. So the temperature in Kelvin, remember, to get Kelvin temperatures, we take the Celsius temperature, 28, and we add 273 to that. Technically 273.15, but you don't have to be that precise. The 0.15 is not going to affect your answer enough to cause it to be wrong. Not even close. So 301 K is close enough for the temperature. And then we're going to divide by the volume. The volume has to be in liters. So typically volume units are going to be either milliliters or liters. Not much else will give you. So 256 milliliters, and then 1 liter is 1,000 ml. So that's going to be 0.256. So that's what we'll put down here. And so at this point we have everything we need, and the units are correct. So moles cancels out. I'm sorry, atmospheres don't cancel. That's what we're gonna get. Sorry, jumped the gun there. Liters cancels out, and then the temperature Kelvin. So that's going to give us a pressure in atmospheres, which numerically, arrow down here, works out to. So give me a second. All right, assuming I did that correct, I get a pressure of 0.761 atmospheres. The problem wants it in torr though, so we do have to do a conversion. So we got the correct pressure, but it's in the wrong unit, atmospheres, from what this problem asked for. Typically, it's easiest to do the conversions at the end because we don't want to have to worry about changing our gas constant R. We just want to use that standard value. So in this case, we're going to have to convert. We have 0.761 atmospheres, and then the common conversion factor that we used in the last one, 760 torr per atmosphere. So we get 578. All right, and that's what we would get. They said no units, of course, in Blackboard, but that's the correct answer there. Okay, so this was one type of ideal gas problem where we're just going to use PV equals nRT and solve for an unknown. In this case, only one of those can be unknown. The other major type, though, is going to be what I'm going to go through here, where we're going to be changing one or more of those parameters. So we have a 23.2 liter sample of air, and it's cooled from 89 degrees Celsius to 17 degrees Celsius. So we know already that one of those parameters, in this case the temperature, is changing. And then it says the pressure is maintained at 2.85 atmospheres. What is the final volume in liters? All right, so in a problem like this, we are going to still start with PV equals nRT, but then what we're going to do is we're going to take all of the parameters that are constant, move them to one side, and all the parameters that are changing and move them to the other side of the equal sign. Just do a little bit of algebraic manipulation on this equation. So in the problems like this, basically, if we tell you it's constant, it's constant. If we don't tell you anything about it, then you would assume that it's constant. So in this case, the pressure is maintained at 2.85 atmospheres. So that means pressure is constant. I'll put a little X by it to indicate that it's constant. We don't know how many moles there are, but it's a sample of air. We're not telling you that we're changing the amount of air that we have, so we'll assume that moles is constant. Again, typically speaking, if we don't say anything about one of the values, that you would assume is constant, and then the universal gas constant R is always constant. So the only thing in this problem that's changing is volume and temperature. Temperature, we gave you the numbers, we gave you the initial volume, and you're trying to find the final volume. So it's only volume and temperature. So we're going to move those over to one side of the equation. Doesn't matter how we rearrange it, but we'll do V over T. So we'll divide both sides by T, and then we'll divide both sides by pressure to move pressure over to the other side. So we'll get V over T is equal to NR over P. So just rearranging this equation, these are all constants, so that means this ratio V over T is a constant. Okay? And what that means we can do is then we can take this ratio V over T and say that the initial and final ratios have to be equal because they're set equal to a bunch of constants. So V1 over T1 equals V2 over T2. Okay? So this is a statement of, I believe, Charles's law, if I'm getting those laws straight in my head. Volume as a function of temperature is Charles's law. But we don't have to necessarily memorize that. We can just, again, start with PV equals nRT and just isolate the variables that are changing and isolate the ones that are constant on the other side. So we get V1 over T1 equals V2 over T2, and then from here we can solve for final volume, which we'll call V2. It doesn't really matter what we abbreviate as V2 and V1. So V2 is going to be V1 times T2 over T1. Okay. In problems like this, it doesn't really matter what volume unit we use because it's whatever unit we have on V1 is going to be what we solve for V2 in, but we do need to make sure, again, that temperature is always in Kelvin. So T1 in Kelvin is 89 degrees Celsius plus 273. So that comes out to 362 Kelvin for T1. And then T2 in the correct units. So very often we'll give you this 17 Celsius, and then we add 273, and that comes out to 290 Kelvin. So we don't typically give you the temperatures in Kelvin, or very often we don't. So you have to convert them, and now we're ready to put everything in. So V1 is 23.2 liters. T2, the final temperature is 17 Celsius, which is 290 K. T1 is 362 Kelvin. And so temperature units divide out, and we're going to get an answer in liters. Hang on just one second. All right, and what I got was 18.6. All right, the volume decreases as the temperature as the temperature decreases also. All right, so this is the other type of problem where you have to basically figure out which variables are changing and move them over and set initial and final equal to each other. All right, so a couple other variations on that same theme then, because that was one of the major problem types we had in this assignment. So this is a multiple choice question, which is sort of more in relative terms. So what is the effect of the following on the volume of 1 mole of an ideal gas? All right, so again, N is constant, 1 mole. The pressure changes from 760 torr to 202 kilopascals, and the temperature changes from 37 Celsius to 155 Kelvin. So the real challenge with this problem, I think, well, one of the challenges is getting the units right because they're all different, 2 different pressure units, 2 different temperature units. But the approach we're going to use is the same as the last problem. PV equals nRT, and we figure out which ones are changing. So we have 1 mole of an ideal gas. We're not told anything about that changing, so that's going to be constant. And then R is also constant. But in this problem, pressure, volume, and temperature are all changing. So we're telling you the pressure is changing from 760 torr to 202 kilopascals. We don't know for sure if that's changing, but there's 2 different numbers there for pressure. And then the temperature goes from 37 Celsius to 155 Kelvin. Again, 2 different temperatures that we have to consider. So pressure and temperature are changing, and we're trying to ask you about the effect on the volume. Now, we don't know the initial volume, but we are asking you about the effect of it. So what we're going to do is we're going to move the units that are changing over to one side. And so that means we're going to take temperature, we're going to divide both sides by temperature and say that PV over T equals to NR, which is constant. And what that means then is this ratio, PV over T, is going to be constant. So P1 V1 over T1, that ratio has to equal the final P2 V2 over T2. Now what we want to know here is we want to know how does the volume change, although we don't know what the initial volume is, so we're not going to be able to get an exact number, we're just looking for the relative change. So what we're essentially going to solve for here is we want to solve for the ratio V2 over V1 and figure out what is the relative change in volume from the start to finish. And so we're going to rearrange this equation to solve for V2 over V1, and so what that's going to end up as is P1 T2 over P2 T1. All right, so it's going to require some algebra to get there, so make sure that you got that, but basically we want V2 over V1, so we're going to move V1 over here, and then P2 is going to cross over to the denominator, T2 over to the numerator. Okay, so this is the ratio we're considering, P1 T2 over P2 T1, and that's going to allow us to identify which of these 5 answer choices is correct. So we're going to have to start putting numbers in, but we have to make sure they're all in the same unit. So P1 and P2 have to be in the same units if we're going to divide them by each other, and then T2 and T1 have to be in Kelvin for this to work. So it doesn't really matter which unit we use for pressure, we just have to choose which one we like. I'll go with torr because it's the more common one, I suppose. So P1 we're going to put in is 760 torr. And then we have to calculate P2 in torr. So we haven't gone through kPa yet, but this is the other pressure unit we expect you to know. So the final pressure, 202 kPa in the correct unit of torrs, is going to be, we have 202 kPa, 1 atmosphere is 101 kPa, or 101.3, we don't need to be that precise for this problem. And then we have 760 torr per atmosphere. So there is a direct conversion between them, but I don't know what that is, so we'll just use it in 2 steps. We'll go 202 kPa to atmospheres, that's 2 atmospheres, and then times 760 torr, so that's going to be 1520 torr is P2, so it's going to be 1520 torr in the denominator. And then in the numerator we have the 2 temperatures, which have to be in Kelvin. So T2 is the final temperature, which is 155 K. And then T1 is the initial temperature, 37. If we convert that into Kelvin by adding 273, that should be 310. Double check that. All right, 310 Kelvin. Okay, so that's going to be the ratio then, and what this comes out to is 760 over 520 is 1/2, and 155 over 310 is 1/2. So this whole ratio, all the units dividing out, comes out to 1/4. So what that means is that the ratio of V2 over V1 equals 1/4, or in other words, V2 is only 1/4 times V1. So if we cross that over, V2 is equal to 1/4 V1, meaning that the final volume is only 25% of the original, which would be choice B. Okay, so in this case we don't know exactly what the 2 volumes are, but the ratio V2 over V1 is going to be 1/4, meaning that the final volume is 4 times smaller, or 25% of the original volume. All right, so that's the same type of problem, just sort of framed in a little bit different terms. And then this last one here is sort of a more standard one dealing with numbers. We won't deal too much with problems like this where it's going to be sort of in relative terms. Usually we'll have you just find the number like we do in the other ones, but that's we'll end with this one here, which is a little bit more complicated because we have more parameters that are changing. So we're looking again, volume of a gas is what we're calculating. Sample of carbon monoxide, the identity of the gas doesn't matter though for ideal gas equation. We have this temperature and pressure, and then if it occupies 12.7 liters at 295 K and 325 torr. So basically everything is changing. So in PV equals nRT, we have a sample of gas. We're not telling you that the number of moles is changing, it's the same sample. R is always a constant, but once again, pressure, volume, and temperature all changing. So just like in the last problem, we're going to get this equation here, P1 V1 over T1 equals P2 V2 over T2, where we have initial and final set equal to each other, removing everything that's constant. So that's what we're going to do, and then what we're solving for is V2, where this is T2 and P2, and then what we have is V1, T1, P1. So we have everything we need, we just have to solve for our unknown, which is V2. So V2 is going to be, if we just cross multiply, we're going to get P1 over P2, and then we have V1 over V2, sorry, not that, sorry. P1 over P2, and then T2 over T1, and then V1 in the numerator. All right, so let me double check that I did that right, that looks correct, and then we're going to start putting numbers in. And so the key here for units, which we always have to pay attention to in these types of problems, P1 and P2, they can be whatever they want as long as they're the same, because it's a ratio of 2 pressures, so it doesn't matter what units we choose. They're both given to us in torr, so let's go ahead and just use that. So it's going to be 325 torr for P1, and then 565 for P2. And then the temperatures, though, have to be in Kelvin. So we need T2 over T1. T2 is in Celsius 43, so we need to convert that to Kelvin by adding 273. That should be 316. And then T1 in the denominator is already given to us in Kelvin, so it's 295. So temperature has to be in Kelvin. That's non-negotiable in these problems. And then V1, our initial volume, again, whatever units we choose for V1, is going to be the units that we get for V2 is given to us in liters, so that's what we'll use. All right, so torrs cancel, Kelvin cancels. We're going to get a volume in liters. And so when we work this out numerically, if you'll just give me a second. All right, what I got was 7.82 liters. Let me double check that, just because there's a lot of numbers there and I might have messed something up. Yep, so the numbers work out as long as I put the right things in. So P1, P2, T2, T1, V1, good. Okay, so this should be the right number. This problem had variable inputs, so you would not have gotten the same pressure and temperature and everything that I had here, but the approach would be the same, and you enter your number in as whatever we specify, which I guess was 2 decimal places probably. Okay, so that's going to be how we deal with that one. So very similar to the previous ones, just a little bit more involved with more numbers to keep straight. All right, the next two we're going to deal with are going to be density. So for gas density, we sort of have two related parameters. So molar density, which is moles divided by volume. So remember, density is something per volume. The more common form of density that we already know is just what's called regular, just density usually, or sometimes mass density. That's going to be the mass divided by the volume. So there's two different densities we can calculate for gases. This first problem here deals with molar density, although that's not the most common one you'll have. I mean, we don't deal with molar density very often, but in this problem we have it. So on a certain winter day in Montana, the average atmospheric pressure is 747 torr. What is the molar density when the temperature is 17 Celsius? It's actually pretty warm for winter in Montana. Probably should have picked a lower temperature than that. This again had variable inputs, so you would have gotten possibly different numbers. So in this problem here, we're solving for molar density, which is moles divided by volume. And again, the starting point is going to be PV equals nRT. And all we're going to be doing here, I think this problem is not as difficult as you might have thought when you just looked at it. Molar density is a new parameter for us, but it comes right out of the ideal gas equation. So molar density is moles over volume, which is the same thing as N over V in the ideal gas equation, where we use N to abbreviate number of moles. So all we're going to do is we're going to start with PV equals nRT, and we're going to solve for N over V. So N over V, if we rearrange this equation, is going to be equal to pressure over RT. Okay? So we're just rearranging the ideal gas equation, and this is all we need to do for this problem. But because we're using R in the calculation, we need our pressure to be in atmospheres. So when we put this in, and then the temperature still has to always be in Kelvin. So the pressure in atmospheres is 747 torr, and then 1 atmosphere, 760 torr. All right, so always make sure that we're mindful of units in any problem. I'm harping on it all semester, probably sound like a broken record at this point, but it's especially important in this chapter. So that's going to be 0.982. Or 983 atmospheres, and the temperature we just have to add 273. So what we're going to get then is 0.983 atmospheres, and we're going to divide that by R, which is 0.0821 liter atmospheres per K mole. And then the temperature, 17 Celsius, is going to be 290 Kelvin. All right, so when we divide these, atmospheres cancels out, Kelvin cancels out, we get 1 over liters over mole, which is moles per liter. So that's going to give us that ratio in the correct units, and it wants it in moles per liter, so that's what we're going to keep it as. So we get pressure divided by R divided by temperature, and so what I got was 0.0413 moles per liter. Okay, so this would be the molar density. Basically, how many moles of gas are in 1 liter, 0.0413 at this specific temperature and pressure. All right, this number is going to depend on both temperature and pressure, so that's not going to be a constant for this gas or this sample of air as it is. It's going to be dependent on those two variables. But this how you get it is just PV equals nRT, solve for the ratio N over V. Now the other type that's more common, which I'll do now, is going to be dealing with the regular density for a gas that's usually going to be in grams per liter. So what we have in this problem is we want the density of CFCl3 at 32 Celsius and 1.56 atmospheres. So believe it or not, it sounds, though this is something totally different. Now we have to deal with density in grams per liter. How do we approach that? It still comes from the ideal gas equation, believe it or not. So we're going to start with PV equals nRT. We're going to get to an equation for density that you're welcome to memorize, but you can always derive it from PV equals nRT. And all we're going to do in this is we're going to recognize that N, which is the number of moles, can also be written as the mass of the gas divided by its molar mass. All right, that's one of the definitions of moles that we learned back in chapter 5. So what we're going to do is we're going to rewrite PV equals nRT as PV is equal to mass over molar mass times RT, and then density is going to be equal to mass divided by volume. That's the definition of the regular density, mass density, and that's going to be pressure times RT. Sorry, I said the algebra. Pressure times molar mass divided by RT. Okay, so that's going to be the equation for the density of a gas, pressure times molar mass over RT. And so we're just going to put in the numbers, and they have to be, since we're using R, pressure has to be in atmospheres, temperature always has to be in Kelvin, so we're going to use the pressure directly that's given to us, 1.56 atmospheres. We need the molar mass of CFCl3. I'm not going to go through the calculation of that, but it's going to be carbon plus fluorine plus 3 chlorines. And so if you'll give me a second, what that comes out to is (137.36) grams per mole. So that's molar mass, and then we're going to divide by RT. R being the same universal gas constant that we've used a lot in this assignment. And then the temperature has to be in Kelvin. 32 Celsius converted to Kelvin is 305. All right, so those are the numbers. Atmospheres cancel out. Kelvin cancels out. Moles cancels out, so we get grams per liter, which is what we want, so we don't have to do any conversions after this. And so we get 1.56 times the molar mass so what I got was, this number seems large, let me double check it, 8.56 grams per liter. All right, so I got that number 8.56 again, so that seems to be correct. Now you might think that, oh, that number is big, like gas is 8 times more dense than water, but this is grams per liter. Remember that water is 1 gram per milliliter. So gas densities, they do depend on pressure and temperature, but they're typically going to be several hundred to even 1,000 times smaller than a typical liquid density. So gases are a lot less dense than liquid. That's one of their key properties. This is how you calculate the density, and usually for a gas, we report that in grams per liter, whereas for liquids and solids, it's usually grams per milliliter or grams per cubic centimeter. All right, so that's how we do it, though. It's just going to be, this equation. If you want to memorize it, fine, but it's derived from the ideal gas equation. Density is pressure times molar mass divided by RT. And that's how we would calculate density of any gas. All right, the last problem here deals with gas stoichiometry. We did pretty well in these for the most part, but there's just a couple, or just one in this case, that I want to go over. So how many liters of hydrogen gas can be produced at 18 Celsius and 725 millimeters of mercury when 3.75 grams of lithium reacts with excess water. So there's a lot of variations on gas stoichiometry problems. Sometimes all of the reactants and products are gases, or some in this case only one of them is, which is the hydrogen, which should be shown as a gas, but anyway, that's a gas. And we're going to typically, for gas stoichiometry, in a lot of cases, you're going to use regular stoichiometry approaches that we learned back in chapters 5 and 6, along with the ideal gas equation. So it sort of blends those two things together. All right. So we want to know, in this case, how many liters of hydrogen gas can be produced at this temperature and pressure. And what we're going to basically need to do here is we're going to set up a stoichiometry problem first to figure out how many moles of hydrogen are produced, and then we're going to put that back with the ideal gas equation. So first we have to balance the equation. Lithium plus water goes to hydrogen and lithium hydroxide. So we're going to have to, I believe, have, let's see, I think we need a 2 there, 2 there, and a 2 there. That should balance everything. So make sure your equation is balanced. 2 lithiums, 2 oxygens, 4 hydrogens on each side. That looks good. So this is the balance equation, which is important because we need to know the mole ratio between lithium and hydrogen, because we're telling you how much lithium we have, and we're calculating how much hydrogen forms. So what we're going to do first is we're going to calculate the moles of H2 that form. And this is just a mass to mole stoichiometry problem. So we have 3.75 grams of lithium. We're going to convert that to moles using the atomic mass of lithium, which I forgot. I think it's 6.94, but let me double check that. 6.94, good. So we're going to have 6.94 grams of lithium in 1 mole. So that gives us moles of lithium, and then to get moles of hydrogen, we're going to use the coefficient. So we have a coefficient of 1 in front of H2, or no coefficient given, and then a coefficient of 2 in front of lithium. So 1 mole of hydrogen is going to form for every 2 moles of lithium. So this part is just chapter 5 stoichiometry. Hopefully we haven't forgotten it already, because it's important in all of chemistry. So what we're going to get then when we do this is we get 0.270 liters of moles of H2. Wow, got ahead of myself there. That's moles. That's not equal to liters. That's moles of H2. And now what we're going to do, this again is going to be N in the PV equals nRT equation. And we're going to solve for the volume of that in liters. So we're going to solve for volume, which is nRT over P, and we just start putting the numbers in that we have. So N, as we just found, we're forming 0.270 moles. R is the universal gas constant. Temperature has to be in Kelvin, so as usual, it's given to us in Celsius. So we're going to convert that into Kelvin, 291, 18 Celsius plus 273. And then the pressure has to be in atmospheres, so we're going to take this number, 725 millimeters of mercury, which is the same as 725 torr, and we're going to divide by 760. So the pressure in the correct units would be 0.954 atmospheres. So because we're using R in this calculation, which is in liter atmospheres per k mole, the pressure has to be in atmospheres. So moles cancel, Kelvin cancels, atmospheres, so we're going to get a volume in liters, which is what we want. And so what that comes out to numerically, if you'll give me just 1 second. What I got was 6.76 liters. I think this one also had variable inputs, so the number that you might have had was different because you might have had different amounts of, or different pressures and temperatures anyway. But at the same rate, this is how you would do it. So this is gas stoichiometry, but all it really is a regular stoichiometry problem, and then followed up by using the ideal gas equation to figure out volume. So the ideal gas equation gives us a new relationship involving moles, and so that's something that we're going to occasionally use in concert with stoichiometry. as sort of another way of relating moles to a different amount of substance. All right, so that takes us to the end of what I wanted to cover today. There's going to be another homework assignment on this same chapter, which will probably deal more with what's called, a topic called Dalton's law of partial pressures, as well as the kinetic molecular theory of gases, more at the molecular level. So probably a little bit more conceptual next time, but still some numerical problems that we'll tackle next week. So please let me know if you have any other questions on this assignment or anything else related to the course. And I'll hopefully see you guys online sometime soon. Obviously not in person, but hope you're all doing well. And again, don't hesitate with any questions that you have.